Hi everyone, my name is Adam and I'm here to present you my paper co-authored with Armando Castaneda from Mexico. So I'm from Toulouse, and our paper is about K-set agreements, round-based models, and combinatorial topology. So we'll see how these three ideas relate to each other. But first, I want to give a quick reminder about message passing models in distributed computing. So we have processes, we have communication links, and message sent in these communication links. And so the thing is, we might have a lot of different variation on this backbone. So maybe the clocks are synchronized, maybe they aren't, and we have asynchrony. Maybe process can fail, or message can be lost, or communication links can fail, or a lot of other variations. So I give some parameters here, and I'm pretty sure you can think of others. And the thing is that so having multiple models is kind of a staple of distributed computing, because distributed computing is about uncertainty and about what we can do despite this uncertainty, and the uncertainty take many forms. But the issue with having that many parameters is that we cannot compare them, or we have a lot of difficulties comparing them, because most of these parameters are not mathematically formal, and when we formalize them, we don't formalize them in the same way, and so that's a problem. But there is a solution that has become popular in the recent literature, which is using rounds. So I assume everybody knows what a round is, but I'm still gonna give a quick reminder once again. So every process has a round number, and repeatedly each process broadcasts message tag with this round number, wait for some messages, not necessarily all messages, but some messages, and then use these messages from the round to compute the next state message to send. So one subtlety here, if you're coming from maybe the distributed complexity theory parts, for rounds don't necessarily mean synchronous rounds that are in lockstep. We might have asynchronous rounds where processes are different rounds. But thanks to a property called communication closeness, which is you only use message from the current round, even if the message was received earlier or thing like that, you can ensure that basically the system behave as if it was in lockstep. So it doesn't really matter as long as you have this kind of rounds, whether you're synchronous or asynchronous. And there are multiple models using rounds. So for example, the synchronous model is message adversaries, the herd-of model, the dynamic networks model, and I'm sure I'm forgetting some. And one thing that is common with all these models, and that is the thing that interests us, is that an execution in this model can be, or the communication of an execution can be captured by an infinite sequence of communication graphs, where a communication graph is a graph for a round, such that it's a directed graph, and an edge from P to Q means that Q received the message from P at this round or before this round, in the case of asynchrony. And so this means that instead of having something that is either formal but very specifically to the model, or informal and kind of in English, we have a common abstraction, which is this infinite sequence of graphs. And so a model, a predicate, a property, an adversary is simply a set of possible sequences that tells you what can happen. And when we describe it that way, then we have a lot more power to compare, to think about the links between these different models. But there is some issue, and the issue is there are not that much results using this kind of models with infinite sequences of graph. And the results that we have, for example, in the models before, tend to be very specifically tailored to both the problem at hand and the specific properties of rounds. And so that means that we don't necessarily know how to use big techniques that you can apply to a lot of problems and to a lot of round-based models. Maybe an exception, as I say here, is the recent paper by Nowak et al. About characterization of consensus. But the thing is, what we're trying to do here, what we want to do is to start looking for a general technique that help us prove results in round-based model. And so we need two things. We need an approach because we're not necessarily going to start from scratch for this technique, and a problem to study. So the approach is the combinatorial topology approach to distributed computing. If you're not familiar with this approach, what you need to know basically is at each point, instead of configuring a specific configuration, we consider all the possible configuration at this point. So at the input, after one round, after two rounds, after this kind of thing, and at the end. And all this configuration together, gluing them in a meaningful way that builds a combinatorial object called a simplicial complex. And the thing that is interesting is that a simplicial complex has these geometric properties, these topological properties that actually translates to solvability, computability, complexity results, which is really cool. So yeah, and here's the definition of simplex and complex, but you can also look up the book of combinatorial topology approach to distributed computing. Okay, and the problem is k-set agreement. Why k-set agreement? Because k-set agreement is a generalization of consensus, and as I said before, consensus is solved for these round-based models. So what's the difference? The difference is that in k-set agreement, instead of having to decide only one value for every process, the set of decided value might be of size at most k. So it's a weakening of consensus, but it's not telling you can decide whatever you want. There still are constraints, and the number for k for which you can solve k-set agreement tells you something in sort of a hierarchy about the power of agreement of your model. So that's one reason, and another reason is that k-set agreement is one of these problems for which the combinatorial topology approach has proved very, very useful. Because the thing that is pretty amazing is that this combinatorial object I talked about before, which are the simplicial complexes, these objects, if they are k-connected, so it's a certain form of connectivity on higher dimension, about having holes of higher dimension, then you cannot solve k-set agreement on the model that corresponds to this complex in some sense. And so this mathematical property is actually linked with the solvability of the problem. So now we can define actually the models we're going to use and the sort of specificity of this approach. So first, like this definition, basically what I said before, a round-based model is a set of infinite sequences of graphs. That's all. Next, we have an oblivious round-based model, which is different. So an oblivious round-based model is saying, okay, you have an infinite sequence of graph, but actually it's not just like handpicked sequence of graph. It's just you took a set of graph and you said, okay, I want all the sequences where at each round the graph is one of those. So that's the omega of this alphabet in some sense. And so this kind of, it only constrains what can happen at each round and not the succession of rounds. It cannot say something about if this happened at round R, then this must happen at round R plus 1. So it kind of captures the idea inherent in safety properties that nothing bad can happen or something good must always happen. Next, we have closed-above oblivious models. So these models are oblivious, but in addition to that, the sets of graphs that define them has a specific property. And this property is that you can find a subset of graphs such that the superset of graphs is all the graph containing one of these graphs as a subgraph. So for one graph G, for example, then you take all the graphs built where you add 0 or more edges to G, and that gives you a set of graphs. And so if your set of possible graph is this set, we say that your model is simply closed above. And if there are multiple G's and you take the union of these sets for multiple G, then it's a closed above model. And so the intuition here is that you have an underlying structure in your graph that is always ensured. So for example, there's always a cycle, a tree, a star, something like that. And among the examples that we have, you have, for example, the asynchronous model with at most F crashes, or the head of predicate with at least one broadcast per round, which is non-empty kernel runs, which is used in some of the paper about the head of model. And so these models are constrained, and in some sense, they do capture a natural class of models, which are the models that ensure that some graph property will hold for the whole execution, or at least one of different graph property will hold at each round. And another thing that's pretty nice is actually, so I said to you that in the combinatorial topology approach, we express the set of all possible configuration as these combinatorial objects that we call simplicial complexes. And you can think them as maybe if you have 3 processes, then a complex is you have a lot of triangles put together. If you have 4 processes, it's a lot of tetrahedra, and that you can generalize to more dimension. And so the structure of this object matters. And the thing is, for simply closed above models, the structure is called a pseudosphere, which is a common pattern in this approach, a common complex that we know in hand that has nice properties. And you can think of it as a generalization in higher dimension of a bipartite graph. So a bipartite graph, you have 2 sets of nodes, which are, you can think of the views for process 1 and the views for process 2. And then you take all the edges, so all the configuration with one view for one from process 1 and one view for process 2. So that's what's on the left here. And on the right, you do the same, but for 3 processes. And so instead of having edges, you have triangles. And if you had 4 processes, then that would be triangle and over and over. And so the complexes that we use here have this form. And for closed above models in general, there are actually unions of these pseudospheres that are nicely put together. So they also have good properties. And lastly, for these models, you have one constraint that is pretty obvious, which is symmetry. And so symmetry simply says that, okay, your set of graphs contain all the permutation of the graph inside it. And so what it ensures is that you're not, the property that your round-based model need to ensure is not P1 does this specific thing, but one process does this specific thing, or, so it's not about specific processes, it's about what happens, so the pattern in the graph. Yeah, so these are the models we're going to use. And next, I'm going to talk about the combinatorial numbers that are really important for our bounds, our proofs. So first, we have something that is really interesting and really important. All our bounds, so we have lower bounds and upper bounds. So upper bounds saying, okay, how on K, on the K for K-set agreement that can be solved. So upper bounds say, okay, for any K, for this K, you can solve it. And so for all K above it, you can also solve it. And lower bound for this K, you cannot solve it. And so for all K lower than that, you cannot solve them. And the nice thing is all these bounds are expressed using the properties of the graph, defining this round-based model, but not using combinatorial topology. So the combinatorial topology is purely limited to the proof side. And what that means is, even if you don't get all the combinatorial topology, you can use this result once you understand the properties of graph that we're using. And so we have these combinatorial numbers that are capture these interesting properties of graph. And we have 2 kinds of combinatorial number, let's say. We have numbers for the upper bounds that captures how far, as I say, how far can a group of processes send their initial values. And so it kind of tells you how far do this set of minimal values will propagate, which helps in deriving algorithm for K-set agreements. And the numbers for lower bounds, which capture sort of the uncertainty of processes and how much they can differentiate between different initial configuration depending on the message they received and this kind of thing. So pretty much all our combinatorial number are inspired by one that is very common in the literature, which is the domination number. And very simply, a dominating set is just a set such that it reaches every other node in the graph. That means. So basically, if you have this set, kind of everyone will receive at least one message from one member of this set. And the domination number is just the size of the smallest dominating sets. Okay, and so the next result, the next number is the equal domination number, which is useful for upper bounds. And so the equal domination numbers, it's not the size of the smallest dominating set, is the smallest size of a set, such that every set of this size is a dominating set. So there's the difference. In the domination number case, you take one set and you say, okay, I have one set that is dominating set of this size, and that's okay. But here, I want every set of this size to be a dominating set. And what this means is the sets of minimal values of that much minimal value will be a dominating set. And so everyone will receive one of that much minimal values. And so if your algorithm decide the minimal value, then it will solve some form of K-set agreement for this number. For the lower bounds, so we have a number that is less intuitive, though the numbers for the lower bounds are slightly less intuitive, unfortunately, which is called the distributed domination number. And what it does is say, okay, you have the smallest I, such that for all subset of graphs of size I, for all sets of subset of processes of size I, too, this subset dominates this graph together. And so it's not that for each graph, this subset is a dominating set, which would be the definition of the equal domination number. No, what it means is for every node in the graph, there is, for every node at all, there is one graph in this subset of graphs, such that one process in this subset reaches this node. And so it's kind of split among all this graph. And so that it's harder to give it a natural sort of meaning. But what it does is it captures the uncertainty about processes on which initial values are out there, which are the initial value of each process. And so actually it sort of quantifies the uncertainty, and this uncertainty has a link with the connectivity of the intersection of these pseudospheres I mentioned earlier. And as I said before, a high connectivity will forbid K-set agreement. And so that's why it is useful. And we're going to see it right now, because now I have the lower bounds for one round. And so this lower bound, so it's a bit complicated, and there's one number, the MT, that I did not describe, but it is a number defined only on the graphs, on the set of graphs. And as you can see, it's not using the combinatorial topology, as I promised. And the thing is, so it's hard to get into details without going into details of the proof, but kind of both of these terms deal with sort of the uncertainty of processes. The distributed domination number deals with the uncertainty of, in the case where the intersection of few complex is very big, and so it kind of overshadows everything. And so there's very little uncertainty, which means that K-set agreement is solvable for very small k. And the empty part actually captures sort of for a set of size t, how much process will hear, what is the fraction of new processes that will hear from this set at each round. And so that gives some information about the propagation of the information, and so about the uncertainty, which is kind of the opposite of this propagation of information, and once again about this connectivity. So that's a lower bound from one round. That's important. So we have this lower bound for a single round and a model, a closed above model generated by S. Next, we want to do that, to use it for multiple rounds. And the trick is to say, okay, if we have multiple rounds, let's say we have 5 rounds, so we have 5 graphs. And what we're going to take is we're going to take the product of this graph and build one graph out of those. And then we can consider it just like it's in the one round case. And so that's how we define. So we define this graph product, which is very intuitive. We say, okay, the graph product is all the edges. If there's like one edge, a path between the two nodes that has a first edge on the first graph and a second edge in the second graph. And we have auto loops so that you don't lose edges by doing the product. And so we do that. So there's a subtlety that is treated in the paper, but I won't go into details here, which is that actually when you do that on closed above model, so you do that for this set of graphs, you lose in some cases the closure above. So this is not maintained by this product. But actually you can do this product in a specific way that ensure that you have the properties that are needed for the proofs, which are things like containing a pseudosphere or a union of pseudosphere and other things. And so we can actually do that even if this closed above property of the set of graph is not maintained by products, by self-products. And there's also another subtlety, which is for the one-run case, we actually, we don't constrain the algorithm at all. So it can be any algorithm. But here, because we collapse like 5 graphs into one, we have lost some information, which is the path of the messages. We only say, okay, a process that receives a message know which process send it to him and to it, and what is the initial value. And so that's only the information that is available. And so we call this algorithm Oblivious because they forget everything about who sent them which message, except the pair's process name and initial value that they know of. So it's constraining a little bit the multiple run cases, but the one run case apply to any graph, any algorithm. And also, so I'm not going to go into details, and the upper bounds are not using mostly the combinatorial topology, but we also have upper bounds using this equal-domination number or the covering numbers, which are some numbers depending on this equal-domination number, and this also generalizes to multiple round on the same conditions. So to conclude, in the paper, what we have given is we have lower bound and upper bound on k-set agreement that are stated only using graph properties, so not using the combinatorial topology. We have a study of the topological property of complexes for some interesting class of round-based model, which are the closed above model. And so we have examined what complexes they give rise, they create, they generate. And so this will be useful for further study of this class of round-based models. And this is one of the first steps to apply this combinatorial topology approach in general to round-based models. And the thing that we can do and we will do to go beyond is first, so oblivious models are interesting, but they are limited, obviously, because a lot of properties such as synchrony, for example, rely on the constraining one round depending on past rounds. And so it's really useful, but that means that in some sense, the difficulty here is you need to change sort of the protocol at each round instead of saying, okay, I'm going to apply the same transformation at each round, because the transformation will depend on what happened before. And so that's what's harder, but it's definitely an important endeavor. And lastly, these combinatorial numbers that we have, we think that there are a lot more to unravel about them, and understanding how they relate to each other for families of graph and things like that would give us information about the tightness of our bounds, which is an important information to have. Thank you for listening to me, and have a nice PODC conference.